Let's start week 13 of Modeling with Statistics. This week, we're going to learn regression analysis. What is regression analysis? Before talking about regression analysis, let's review what is correlation analysis. We've already learned about correlation analysis. With a correlation analysis, you can measure the strengths of the association or relationship between the numerical variables or parameters. So dataset 1 and dataset 2, how strongly they are connected to each other. That is all about correlation. Now let's move to regression analysis. When you do a regression analysis, you have to find two parameters or two datasets which has correlation. With these two parameters, you can do regression analysis. Once you do regression analysis, you can determine a formula, or you can say mathematical model between the two parameters. As an output of the regression analysis, you can get this kind of the formula, y equal ax plus b. This means the value of y is calculated multiplication of a and x plus the value of b. The a is called slope. The b is called y-intercept. So the goal of the regression analysis is to find a number for a, another number for b. Then you can show the relationship, numerical relationship or formula between y and x. Again, the first step of the regression analysis is to find a data, y and x, which are correlated each other. Then run the regression analysis to get the formula to show the relationship between y and x by finding the numbers of a and b. I will demonstrate how to do it in a class after this video. This is an example of the regression analysis. For example, this is a relationship between revenue and the temperature. Okay, the good example of this case is beer, sales of beer, or the ice cream. Okay, let's take an example of the ice cream. So you have the sales revenue data. Also, you have the past temperatures of each day. With these two data sets, you can know the correlation by calculating correlation coefficient. And now let's assume these two parameters, revenue and temperature, has a strong correlation. That means the higher the temperature is, the higher you get the revenue or sales. This is positive correlation. Now you run the regression analysis for these revenue and temperature data sets. And here is an example of the output of the formula from the regression analysis. Let's see this example. Revenue equal 312 times temperature plus 45,000. Now you get the formula between the two parameters, in this case revenue and temperature. And with this formula, you can apply many problem solving or forecasting or many business planning. There are many practical ways to apply this formula. Let's look at some other examples. But before that, let's see more other examples of the regression analysis. Here are some examples of regression analysis, or some types of the relationships of the two parameters. The first one, the upper one, left-hand side and right-hand side, these are the correlation because the relationship between y-axis and x-axis is linear or straight line. You already know this is correlation, positive one and negative one. But this may not be the case in general. We focused only on the correlation with a linear relationship, but in this world there are many other relationships. For example, let's look at the chart in the middle. Left-hand side, this is almost flat relationship. That means no relationship or no correlation. How about the right-hand side? This is not a linear or this is not a straight line. This is a kind of curve like this. This is called a positive curvilinear, and the relationship between y-axis and x-axis is described with log, mathematical log. And also, you can see the bottom ones, the left-hand side, this is U-shaped curvilinear or parabolic relationship. Yes. Is there any correlation in it? The answer is no, because this is not a straight line at all. But you can see a relationship, the curved relationship like this, U-shaped relationship. So you can say, yes, y-axis and x-axis is a relationship, but this is not a correlation. You can say the same thing on the right-hand side. This is an exponential curve. And if you describe the relationship between y-axis and x-axis, you have to apply exponential formula. Although we have this kind of many types of the curves or relationship, we just simply focus on the linear or straight line relationship, which is correlation, simply because it is way simpler to have to calculate the formula y equal ax plus b. Once you get this simple formula, you can easily apply this formula to many cases. So, in this class, let's focus on the correlation types of datasets. In other words, linear correlation dataset. This is how it works. I will demonstrate it in the class after this video, no worries. It's pretty simple if you use Excel spreadsheet. But before moving to the next slide, I'd like to highlight the word Rsquare. This index is used for regression analysis. It is in general called Rsquare, but the official name is coefficient of determination. In Japanese, 決定係数. This is a measure of the usefulness of the regression equation or formula, how useful it is. The maximum value of this Rsquare is 1. If all the original data are on the straight line, no gap from the straight line, In such case, you get 1 for the R-squared. If this data is getting scattered or getting more, or the gap from the straight line, in that case, you have a lower value of R-squared. Or you can take this R-squared index as like this. This means percentage of how much X parameter explains Y parameters. You understand what it means if you look at some example. Here's an example. If you look at the chart, this is an incentive in Japanese yen per unit, and you get the sales result. You have 2, 4, okay, 12. This is a result of every month last year. You have the 12 months result. If you take correlation coefficient, in this case, it is 0.87. That means incentive and sales has a strong correlation, which means if you increase the incentive value, you have more sales. Okay. Once you run the regression analysis, you can get the result or output as a chart shows on the right hand side. You draw a straight line on the scatter diagram, and then you have the formula of Y and X. In this case, Y-axis is sales. X-axis is incentive. So you can replace this formula as sales equal 0.0078 times incentive amount plus 47.843. And if you look at R-squared, this is the 0.76 or something. That is quite high, simply because the original data plot is close to the straight line, but not perfect. If all the scatters, the plot is on the straight line, R-squared is 1. But 0.75 means the original data is not that far from the straight line, so you can rely on this formula. If there are any guideline rules to see how you see the R-squared, there is no rule, so you do not have any strict rule to have the, let's say, it should be more than higher than 0.5 or 0.7 or something like that. But you can check the reliability or usefulness of this formula by looking at R-squares. It is better to have the higher value as an R-square, but it is not necessary that you can say, oh, this formula, you cannot use this formula because simply R-square is 0.3. Nobody say that. There is no rule. But try to find the best fit. That means higher R-squares if you have many choices. Okay, let's go back to this the example. In this case, R-square is 0.75. That means 75%, or let's say 76%. What does it mean? You can take R-squares, this is as a percentage of the how much incentive explain the sales result. In this case, that's 76%. So you can say, yes, the sales result can be explained by incentive, but this is only 76%. The remaining 24% is something other than incentive to determine the sales result. So then you can say, yes, if the incentive can explain 76% of the result, sales result, then we can rely on this formula, although we really don't know what are there for the remaining 24%. So this is very simple analysis, and you can say this is a bit rough, but this is at the same time this is very useful and practical because it's very easy to do and easy to apply in a practical cases. So once you get this result, this formula, these are some sample questions. Try to answer this question. The first one, A, how much unit could you sell if you spent 20,000 Japanese yen per unit as incentive? This is very easy. How about B? How much incentive do you have to spend to sell 185 units? Can you calculate? The last one, if you have another product, not this one, with a formula like this, which product, this product on this slide or this new product is more cost effective? How can you know that? This is very important decision, or this is very important analysis in a business to see which is more cost effective. Try to answer these questions. Take some time. Finally, this is a reminder for you because they are very confusing. What does it mean? If you look at these numbers, first one, correlation coefficient, and the slope in the formula, in this case 0.0078, and R squared. Some students are confused with these numbers. Again, correlation coefficient and R squared, they show the strengths of the two parameters, relationship. Also, you can say mathematically how close to the linear or straight line, in other words, linearity. But if you look at the slope, this is a ratio of the two parameters, in this case, sales and incentive. If you increase the incentive by 5,000, how much sales you can increase? So you can say this slope, 0.0078, shows the ratio between y-axis and x-axis. At the same time, in this case, you can say the effectiveness of the incentive. You can see the slope of the straight line. This number, 0.078, shows this slope. If the number is higher, you can see the steeper slope. This slope shows the effective or ratio between x and y. So please rephrase, what does it mean in this case? This slope shows. Okay, this is the regression analysis. We will do some exercises and I will demonstrate how to do it with an Excel after this video.